Section 2.5 covers homogeneous and Bernoulli equations. So in this section, we're going to start with a homogeneous first order equation and define what a homogeneous, should not be repeated here, first order equation is. We'll talk about the method used to solve it, and then we'll work out an example. And then we'll go to the Bernoulli equation, again, define it, talk about the method used to solve it, and then work out an example. And then I have, I think, 4 equations that we'll look at and classify as to what type of equation that each one of those is. So we'll start with, sorry about that repetition, a homogeneous first order equation is an equation that can be written in the form dx over dy equals f of xy, where f of tx, ty is equal to t to the n f of xy. So a homogeneous function is, this is the definition, is one in which if you replace each variable with t times that variable, then you'll be able to factor out t to some power. And you get t to some power times that original function for any value of n could even be 0. N could be negative. But for some value of n, you could factor that out. So for example, here we've got xy dy equals x squared plus y squared dx. So here I want my derivative by itself. I'm going to start by dividing both sides of the equation by xy. So, and by dx. So that this equation becomes dy over dx equals x squared plus y squared over xy, and those dx's will cancel. So in this case, our function of x and y is x squared plus y squared over xy. And to see if this is homogeneous, I'm going to replace each x with tx and each y with ty, so that x squared becomes tx squared and y squared becomes ty squared. And then x times y is going to become tx times ty. When I simplify this by squaring each of those terms in the numerator, I get t squared x squared plus t squared y squared. And in the denominator, I'll multiply those t's together to get t squared times x times y. So notice that you could factor that t squared out of the numerator to get t squared times x squared plus y squared. And in the denominator, I have t squared times x times y, and I can cancel out those t's, or the t squareds. And this is equal to x squared plus y squared over xy, which is my original function. So I saved a little space there so I can show you that this is homogeneous. You could write this as t to the 0 power times f of x and y. So this is homogeneous order 1, or order 0 rather. because that power is 0. So if you have a homogeneous ODE, you can solve it. And to solve it, you make a substitution. Let y equal u times x. And then for my derivative, I would substitute in here, I should say, where u is equal to a function of x, u of x. So when I take my derivative, I have to use the product rule for derivatives. The derivative of u is u prime. I get u prime x plus the derivative of x is 1. And so I get dy over dx is u prime x plus u. And that's what I would substitute in. When I substitute, the equation is going to become separable, and then I would solve it as a separable ODE. And here's an example. Here, this is homogeneous. If I replace each x with tx, each y with ty, then notice I could factor a t out of the numerator. And just like that previous problem, we're going to have these x's canceling out altogether to give us t to the 0 times that original function. So this is homogeneous. I'm going to erase this part. To solve it, I'm going to zoom in so I have space. I'm going to let y equal u times x. And then dy dx becomes, let me write this as du dx times x plus u. And when I substitute in, replacing my dy dx with du over dx times x plus u equals, on the right side, I have x plus y, x plus, and y is u times x over x. So right away, you might notice that you can simplify the right side. You can factor out that x in the numerator, and those x's will cancel to leave us with 1 plus u. So our equation becomes du over dx times x plus u equals 1 plus u. And then we could subtract the u off from both sides, and those will cancel. So I have du over dx times x is equal to 1. I'm going to write that. And this is separable. It's separable, and so I will solve it by separating the variables. I'm going to multiply both sides by dx over x. That way my x terms will be on the right side. These cancel, these cancel. I'll be left with du by itself. And on the right side, I get 1 times dx over x. We can solve this by integrating. On the left side, when you integrate 1 with respect to u, you get u. I'm going to put my constant of integration on the right side, which when you integrate 1 over x with respect to x, you get the natural log of x, and then plus c. So here I am going to replace my u. We had y equals u over x. And so solving for u, we get u is equal to y over x. Just divide both sides by x. u is y over x equals natural log of x plus c. And then I'll solve for y by multiplying both sides by x. I could keep the right side factored if I wanted to, but I think it looks better when you multiply it out to get y equals x natural log of x plus cx. And that's our general solution. On this section, I don't have any initial value problems for us to work out. So we'll just look at solving these equations. And so every homogeneous equation becomes separable after you make that substitution. You solve this separable equation and then go back and go back and replace the u with, in this case, y over x. So let's move on to Bernoulli's equation, or the Bernoulli equation. The Bernoulli equation looks like this. It almost looks linear. You have dy dx plus p of xy equals q of x times y to the n power, where n is not 0 and n is not 1. If n is 0, then that y to the 0 would drop out and the equation would be linear. If n is 1, then this right side, q of x would be multiplied by y to the first, or just y. And then you'd have these two y terms, which you could combine, and it would be linear. It would also be separable. So Bernoulli. To solve a Bernoulli equation, you let u equal y to the 1 minus n power, and then I usually solve that for y, and then I take the derivative. So we'll wait to do that, but u is y to the 1 minus n power. It'll change this equation to a linear equation. So Bernoulli equation becomes linear. A homogeneous equation becomes separable. Let's work an example. Here's our example. Dy dx plus y equals y squared. Notice that we have our derivative plus p of x times y equals q of x times y to the n power. In this case, p of x is 1, and q of x is 1. And n is 2. So when we solve this, this is Bernoulli. When we solve it, we're going to let y, let me fix that, let u equal y to the 1 minus n power, n is 2. So we have u is equal to y to the negative first power. Then you can apply that negative first power to each side, and it will give you y is equal to u to the negative first. And then I can calculate my dy dx, and then dy dx is the derivative of u to the negative first It's going to be negative u to the negative second times du dx. Remember, and here again, u is a function of x. Because u is defined to be a function of y is a function of x, u is a function of x. Okay, so this is what I'm going to substitute. This and that u equals y to the negative first, which gives me y equals u to the negative first. I think I'll start right here. So my derivative dy over dx becomes negative u to the negative 2 du over dx plus y. Y is u to the negative 1 equals y squared. And again, y is u to the negative 1. So you have u to the negative 1 squared on the right side. So we know that this is going to become linear. And because it's going to become linear, we want that leading term to be just the derivative. For linear, linear is this part of the equation. So I'm going to take whatever coefficient I have of du dx, I'm going to take that coefficient and multiply both sides by it. I'm going to multiply by negative u squared times negative u squared. On the left side, the negatives cancel. U squared times u to the negative 2 cancels to give you u 0, which is 1. So it leaves me with just du over dx. And then negative u squared times u to the negative first gives us negative u. On the right side of the equation, u to the negative 1 squared is u to the negative 2. When you multiply that by u squared, those u's will drop out. It'll give you u to the 0. And so really I just have 1 times negative 1 is negative 1. So this equation is linear. And to solve a linear equation, we use an integrating factor, mu of x equals e to the integral of the coefficient of u, that's going to be negative 1 dx. That gives us e to the negative x. So I'm going to multiply through by e to the negative x to get e to the negative x du dx minus u e to the negative x equals the opposite of e to the negative x. And for a linear equation, once you introduce that integrating factor, you can combine your terms into a single derivative. The derivative with respect to x of e to the negative x times u. It's basically just that first term, but you take the derivative term and just list the dependent variable u. So the right side just carries along. And then to undo the derivative, we want to integrate. On the left side, the derivative and the integral cancel out to give us e to the negative x u on the left side. On the right side, that negative carries, and when you integrate e to the negative x, you get e to the negative x divided by negative 1, and then plus c. So those negatives will cancel. And I'll solve for u, by multiplying both sides by e to the x. That'll give me my u by itself. On the right side for the first term, e to the negative x times e to the x gives me e to the 0, which is 1. And then I get plus c e to the x. So here's my solution to the linear equation, but it's in terms of u and x. I'm going to go back, and here's my u. U is y to the negative first. So I can get my answer in terms of x and y. So I get y to the negative first is 1 plus c e to the x. And then if I raise both sides to the negative first power, I'll write my answer over here. We get y equals 1 over 1 plus c e to the x. And that is my general solution. So on the first test, I've given up to 5 equations to solve. And in some cases, I say take each equation, solve each one using a different method, which means that you need to know how to identify which type they are. It shouldn't take long to identify linear, separable, exact, homogeneous, and Bernoulli. I did share a sheet in our class, and if you refer to that sheet, it does kind of help you identify those types of equations. I do not allow that sheet to be used on an exam, but for homework, you can use it, and while you're practicing for the exam. I think the easiest one to identify is linear. So we're going to use L for linear, S for separable, E for exact, H for homogeneous, and B for Bernoulli. And we'll go through each one separately. So linear, you're looking at the dependent variable, most of the time y. And you're looking at those y terms and asking, are they linear? The first one is the derivative terms by itself. The second one, the y is multiplied by a function of x. So, but it's just y to the first. In the second case, it is not linear. So I'm going to put an L, but I'm going to put an X through it to show it's not linear. And it's not linear because you have a y term in the denominator of a fraction. Sure, that y will cancel with this y squared, but it does not cancel with the x squared. So you'll still be left with a fraction there. On this third equation, notice you have a y squared term. Y squared makes it not linear. And then on this last one, oh, there you go. You have a y squared again. So again, not linear. So the first one was linear. None of the others were. Let's look at separable. Separable says that you can take that derivative, and on the other side of the equation, you can write the right side as a function of x times a function of y. You can separate the x's and the y's. So if you bring that 2 over xy to the right side, you'll get dy over dx equals x squared minus 2 over x times y. Notice that you cannot factor this so that you get a function of x times a function of y. So this is not separable. I'm just going to put s's there, and then we'll go and cross out the s if we need to. Let me do the rest as well. Exact, homogeneous, Bernoulli. Exact, homogeneous, Bernoulli. On a test for an in-person test, I give you those letters and you circle all the ones that apply. For an online test, it'll be multiple choice and you check each one that works. So I'm on number 2 for separable. I do have my derivative by itself, but if I look at the numerator, x squared plus y squared is the sum of squares, which does not factor. So you cannot separate the x's and the y's. Well, 3, I want the dy on top, so I'm going to bring my dx term over. This one will take a little bit of work. It'll give me x squared plus 2xy dy equals 2xy plus y squared dx. That's a dx. And then if I divide by dx and also divide by x squared plus 2xy, it'll give me my derivative equals 2xy plus y squared over x squared plus 2xy. I could factor the numerator into y times 2x plus y. I could factor the denominator into x times x plus 2y, but then notice 2x plus y, x plus 2y, neither one of those will cancel out, and you cannot write them as a function of x times a function of y. So not separable. And I can tell number 4 is also not separable, because if I bring that 3y over, I'll have a y squared and a 3y. We wouldn't be able to factor that. If this were 3y squared, then I would have a y squared in common that I could factor out. And it would be separable, but not with 3y. So exact, you write the function in terms of differentials, identify m and n for exact. M dx plus n dy equals 0, where the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So let me tell you first that every separable equation is exact. It's not true the other way, but every separable equation, none of these are separable, are exact. But that if I had a separable equation here, I could make it exact. So if I write this first equation in terms of differentials by multiplying by dx, then I would have dy. I'm going to move that 2 over x. I'm going to take this and multiply by dx to get dy equals x squared minus 2 over xy dx. And then bring the dy over. I'll get x squared minus 2 over xy dx minus dy equals 0. And now this is written in terms of differentials. M dx plus n dy equals 0. But notice that n, the coefficient of dy, is -1. So the partial derivative of n with respect to x is going to be 0. And the partial derivative of m with respect to y, because you have a y term here, is going to be the coefficient of that y term, negative 2 over x, which is not equal to 0. So not exact. Maybe this one is. If I take cross products, then I'll have xy dy equals x squared plus y squared dx. And if I bring that dy term over, it gives me x squared plus y squared dx minus xy dy, and that's equal to 0. So now this is my m. If I take the partial derivative of m with respect to y, I get 2y. Then if I take the partial derivative of n with respect to x, that's just negative y. So close, 2y and negative y are like terms, but they're not the same. So not exact. Number 3 is written in the exact form that we want it to be in. If I take the partial derivative of m, this is m and n, with respect to y, I get 2x plus 2y, and the partial derivative of n with respect to x is 2x plus 2y. Those are equal, and so this one is exact. So it's exact. That one was linear. And that last one is not going to be exact because this term on the right side has x's and y's, a y squared. That 3y only has the 3y. It just won't work out. So homogeneous we just talked about. One nice way to tell if it's homogeneous is if every term in the equation has the same degree. So for example, this term has degree 0. You have y to the first over x to the first. Those degrees cancel out. It gives you a 0 degree term. And then x squared has a second degree. Not the same. It's not going to be homogeneous. Whereas for number 2, x squared, y squared, and xy all have a degree of 2. That is going to be homogeneous. On number 3, we have xy, y squared, x squared, 2xy. Every term is the second degree. And so that is going to be homogeneous. And on this last term, 3y is first degree. And e to the x y squared, I don't even know what that is because it has that exponential. It's not polynomial in form. Not going to be homogeneous. And lastly, Bernoulli. So Bernoulli and linear are mutually exclusive, meaning, I hope I use that right. If it's linear, it cannot be Bernoulli. If the equation is Bernoulli, it cannot be linear. It could be neither, but it could never be both. This first equation, because it's linear, it is not Bernoulli. The second equation, notice if I take that and rewrite it, let's rewrite it in green. I'm going to rewrite that as dy over dx equals x squared over xy is going to give me x over y plus y squared over xy is going to give me y over x. So if I bring this linear term over to the left side, I get dy over dx minus, let me write that as 1 over x times y equals, on the right side, I'm going to write this as x times y to the negative first. That's that x over y. So notice that this is Bernoulli. That you've got, this is the exact form for Bernoulli. Y prime plus p of x y equals q of x times y to the n, where n is not 1 and n is not 0. In this case, n is -1. So we took number 3 and we wrote it so that it was solved for dy dx over here. But there's no way to simplify this fraction to write it in Bernoulli form. We just can't write it in Bernoulli form. So that's not Bernoulli. And then on number 4, this is written in Bernoulli form. And notice that it is Bernoulli. You have a function, you have the derivative plus 3 times y equals a function of x times y to some power. It's Bernoulli. So let's see, 1 was just linear, 2 was both homogeneous and Bernoulli, 3 was both exact and homogeneous, and 4 was only Bernoulli. There are some equations that could be 4 different types. You can never have all 5 types because linear and Bernoulli are mutually exclusive. And that's section 2.5. I think we spent longer just classifying than solving. But have a great day.